This is an irony, of course, because general relativity has a reputation for being incredibly difficult to understand. The old joke is that Arthur Eddington, the British astrophysicist who was a great popularizer of relativity as soon as it came out, he was asked at a talk, I've been told, the questioner says, there's only 3 people in the world who understand general relativity. Can you tell me who the third one is after him and Einstein? And Eddington hesitated. And the questioner says, oh, don't be so modest. And Eddington says, oh, no, I'm trying to think of who the third person is. This is not true. It was never the case that only 2 or 3 people understood general relativity. It's a language of mathematics that we need to understand, but we can get there. We can get there faster than most people because you've listened to the previous video that we've had about geometry and topology. So you know something about the geometry of curved space and curved space-time already. So for us, it's going to be a breeze. All right, let's go. So let's think about Newtonian gravity first. We've already talked about Newtonian gravity. Professor Newton told us that the force due to gravity looks like Newton's constant g times one mass m1 times the other mass m2 over r squared. The inverse square law of gravity. So you have 2 objects. There is action at a distance in between them. They pull each other together proportional to their masses and inversely proportional to the distance between them. And then Laplace says that you can think of this as the slope. The force due to gravity can be thought of as the slope of the gravitational potential field. So you have some field phi as a function of distance r, and it looks like this, and so you're sitting here, and the slope of that field gives you the force of gravity. It's not a different theory than Newton's. It's exactly the same as Newtonian gravity, but it's put into the language of a field theory, so that rather than simply action at a distance, you have an equation that tells you how the field changes from point to point that is a purely local equation. So that's a step forward. However, this is 1600s. This is around 1800, but then Maxwell comes along with electromagnetism. Okay, Maxwell and other people, but one of the great achievements of Maxwell's electromagnetism in the mid-1800s was understanding that there was a unification of electric phenomena, magnetic phenomena, and also light and radiation. And part of understanding the symmetries of that theory was Einstein's appreciation that the speed of light would be the same to everyone, that you did not need an ether pervading space-time to explain any of it, and the whole theory that we now call special relativity. And the reason I'm bringing these up is, of course, because Newtonian gravity is not compatible with special relativity. So Newton's equation here for the force due to an object with a mass m acting on an object with mass m2, m1 and m2, there's no time in here. The time parameter, the time of the universe, does not appear in this equation, which means that if I move one object very, very quickly, the gravitational force on the other one changes instantaneously, no matter how far away it is. There's no speed of light built into this equation anywhere. And when Maxwell came up with E and M, electricity and magnetism, and then Einstein codified it in terms of special relativity, the speed of light has this really important feature. You cannot send signals faster than the speed of light. If Newtonian gravity were true, you would be able to send signals faster than the speed of light through the force of gravity in some object that you were waving back and forth. So Einstein knew this. He knew that you would have to modify Newtonian gravity. And I think that even before Einstein, probably people appreciated it. They appreciated that the symmetries of Newtonian mechanics were different than the symmetries of Maxwell's electromagnetism. There's Galilean invariance in Newtonian mechanics, and there is Lorentzian invariance in relativity. Those two things are not the same thing. So Einstein thought a lot about how to do this, and there's sort of a general way that you would try to think about how to do this, which is to write down a relativistic field theory. In other words, to update Laplace's theory in such a way that it would give you all the features that gravity had. People tried that. It didn't really work. Nordstrom, among other people, was a person who tried it, but it didn't really work for various reasons. We're not going to go down all those blind paths. We're going to skip right to the right answer. So Einstein comes along after inventing special relativity. Remember, just to put this in perspective, Einstein didn't really invent special relativity. He perfected it circa 1905. He really was the one who understood what special relativity really meant and explained it, got rid of the ether, all that stuff. What we now know as Lorentz invariance was understood at a deeper level. And in that same year, 1905, Einstein suggested that light could be thought of as particles, which we now call photons, and he did other things as well. So he was thinking very much about quantum mechanical phenomena this whole time, and also thermodynamics and statistical mechanics. But certainly after putting relativity together, special relativity in 1905, gravity was foremost on his mind. And he spent around 10 years, 1905 to 1915, understanding how you could fit gravity into the relativistic framework before coming up with general relativity. And the names aren't very good, special relativity, general relativity. It's not really special versus general. It's two very different things. Special relativity, like quantum mechanics or classical mechanics, is a framework. It's a sub-framework of classical mechanics. Everything here is classical, even though it's relativity. We're not doing quantum. Classical means non-quantum, so we're classical for this whole video. So special relativity is a different version of classical mechanics than Newtonian spacetime is, but it's still classical mechanics, okay? General relativity is a specific theory. So once you have special relativity, that's a framework in which you can build many theories, like Maxwell's electromagnetism, like relativistic quantum field theory. The standard model of particle physics is a theory that lives within the framework of special relativity. It's a quantum version, but still the same basic framework there. General relativity is also a different theory that lives within that framework that special relativity sets up. So it's actually in some sense more specific than special relativity. It's the theory of special relativity when you let space-time be curved and you give it a specific way of being curved, and you call that gravity. So his breakthrough, Einstein's breakthrough, came from, as it often did for Einstein, thought experiments. You know, he was a genius, clearly, he's Einstein, but he wasn't the most mathematically inclined physicist around, even at that time. He was the genius at thinking of things physically and in terms of thought experiments that gave you immense physical insight into what's going on. So the thought experiment that he came up with is the following. Take a box, a sealed box that you can't get out of, put a physicist inside this box, okay, and they're doing experiments. And you're giving them the task, find out what are the conditions in which the box is embedded, the bigger outside world, okay? So you could ask, for example, is there an electric field? Here's an electric field vector. Imagine there's some electric field pointing vertically, both inside and outside the box. Could you do experiments inside the box that lets you know that there's an electric field surrounding you in all places? And the answer is clearly yes. And so Einstein wouldn't have put it in these terms, but what we can do is say, look, imagine there's an electron, E minus, and there's a proton, P plus, okay, two different particles with two different electric charges. The way that the sign convention works out, the proton gets accelerated in the direction of the electric field. So the proton gets accelerated vertically upward. The electron will get accelerated vertically downward. So something different happens to the electron and the proton because they have different electric charges in the presence of an electric field. Therefore, if there were zero electric field, they would just sit there. If there's an electric field pointing in some direction, they begin to accelerate in opposite senses along that direction in which the electric field is pointing. So the answer to the question, can you detect an electric field while you're in a sealed box, is clearly yes. So Einstein says, okay, let's play the same game for gravity. Okay? Imagine there's some gravitational attraction, G, pointing downward. Here's your physicist. Okay. Can they do an experiment to detect the gravitational field? And they're in a sealed box. They can't just look outside and go, oh yes, I'm sitting on the Earth, okay? Therefore I know there's a gravitational field. They're not allowed to look outside. Well, you can say, you know, let me take a heavy object and a light object, all right? Two things with different masses and therefore in some sense different couplings to the gravitational field. And you can drop them. But ever since Galileo, we've known that a heavy object and a light object will fall at the same acceleration in a gravitational field, as long as the air resistance is negligible and so on, right? So Einstein says, you know, okay, I can drop two objects, but they're unlike electricity and magnetism. The objects in the gravitational field will always fall in exactly the same way. And you might say, well, still they're falling, therefore I've detected the gravitational field. If I have an object right here and I drop it, I have detected the gravitational field, right? But Einstein, who is smarter than me or you, says you don't know that. What if there's not a gravitational field? What if I've drawn my box better? But instead of that, You're in a rocket ship, okay? Here's the engine of your rocket ship, and so you're accelerating upwards. The same thing would happen, right? You're accelerating upwards, you take these two objects, you let them fall, and they fall at exactly the same rate. In fact, they're not really falling at all. They're remaining stationary, and your box is accelerating up into them. And so what Einstein says is maybe this Galilean result, the two different objects will accelerate at the same rate in a gravitational field, extends more broadly. Maybe it's not just the physics of falling objects. Maybe it's all of physics, he says. Maybe there is no experiment you can do in that box which could actually tell the difference between being in an accelerated box versus being stationary on the Earth or some other gravitational field, okay? So we're comparing stationary on Earth, in our usual way of thinking about it, to accelerating at 1g, 1 Earth gravitational acceleration, but out in outer space, far away from the actual Earth. And we're also imagining you can't hear the rocket engine roaring or anything like that, okay? In that case, Einstein goes on to invent what he calls the principle of equivalence. And in case you're wondering, the equivalence here is between gravitation and acceleration. He says in a small region of space-time, and this is important, okay? In a small region of space-time, sometimes people forget that part. They shouldn't. No experiment can distinguish. I can do better than that. I always try to rush because I write very slowly, and then I become sloppy, and that slows me down. There's some life lesson here to be learned. No experiment can distinguish between gravity and uniform acceleration. So obviously, if your rocket ship is boosting and then stopping and boosting again, you would know that it's a rocket ship. The Earth doesn't do that to you. But uniform acceleration is just like gravity. I knew that was going to happen. There we go. Okay. Can't put a period on the sentence because it's too close to the edge. All right. So that's the principle of equivalence. Einstein says there's something special about gravity, something that is different between gravity and other forces of nature. The only one he knew very well was electromagnetism, but still, this is a special thing. You can tell whether there is an electric field around you. You can't tell whether there's a gravitational field if you're in a small region of space-time. Now, well, the reason why I'm emphasizing the small region of space-time bit is that people, wise guys, keep coming up with proposed counterexamples to the principle of equivalence, and usually it's because they're ignoring the fact that there's the phrase in the small region of space-time. So in a large region of space-time, so let's imagine this is the Earth, and let's imagine that your physicist's box was bigger than the Earth. Here's your box that you're stuck in, okay? So there's an obvious experiment you can do to tell if the Earth's beneath you. You can drop a ball here and a ball here on far distant parts of your box, and they will move towards the center of the Earth. In other words, they will move ever so slightly toward each other, whereas in an accelerated box, they would move exactly parallel. And the same thing is true here if you're truly on the Earth. Literally here in your room, wherever you're watching this, you could drop two things, and in principle, they do not move on parallel lines. They move closer to each other as time goes on, because the center of the Earth is a point toward which they're attracted. But that effect, that difference, goes away in the limit as you're looking at smaller and smaller regions. So already, this phrase, in a small region of space-time, it has a bit of a flavor of calculus to it, doesn't it? Remember when we defined derivatives? So we did derivatives in calculus. We had some function of x as a function of x, and we said, look, there was a curve there, and what you want is the derivative of f at that point, okay? And what you do is you zoom in on it, and then you draw a straight line. And what you say is that as you come closer and closer, as you get to smaller and smaller parts of the curve that you're interested in, you can approximate that curve, no matter how curvy it was originally. As you go to the limit, as you're looking at smaller and smaller regions, it looks more and more like a straight line. So the principle of equivalence is saying something similar about space-time. And in fact, so you can translate the principle of equivalence, P of E restated, or implies, let's put it that way. It's not exactly the same statement, but the implication that Einstein drew from it is that physics in small enough regions, I won't keep writing the whole thing, of space-time, reduces to special relativity. So what he's saying here is the rules of special relativity, by hypothesis, we just don't put gravity in there. Okay, special relativity is not a theory of gravity. But what he's going to say is when we do include gravity, we don't give up on special relativity entirely. We say that special relativity applies in the limit as you go to smaller and smaller regions of space-time. And just like calculus comes about by saying in a small region, when you zoom in on a curve, it looks like a straight line, you can go from this statement that physics looks like special relativity in a tiny region to a statement that resembles differential geometry. Okay? Differential geometry is secretly what we were doing when we did geometry in the previous video. This is the point of what Gauss and Riemann did. Because rather than taking a uniform, smooth geometry everywhere like you would have over a sphere, they said, well, we can look at individual points in some wildly fluctuating geometry and describe, characterize the curvature of the manifold locally at each point. So this is where the word differential comes in. Differential is just a fancy way of saying derivative. This is calculus applied to geometry. So the point of differential geometry in some sense is in small regions, geometry looks Euclidean. So I could have said this in the geometry video, but I didn't say it out loud. But this is the point. So if you have, let's say, a sphere, okay, here's a sphere. One way of thinking about what Gauss and Riemann did, one way of thinking about how they've managed to make sense of the geometry of different curvatures in different places was they said, look, if I take one point on the sphere and I zoom in on it, just like the whole surface of the Earth is roughly spherical, but if I'm in one tiny patch of it, it looks flat, right? That's why there are people who think the whole thing is flat, because they don't understand differential geometry. They don't understand that the small region can look flat, even though the whole region is actually quite curved. And what Gauss and Riemann do is that they actually use their brains to invent a whole mathematical structure here, and they're able to sort of say, in the vicinity of that one point, all geometry looks exactly Euclidean. In the limit, as you, in a curved manifold, go to smaller and smaller regions, you look more and more like there's no curvature at all. And then you can build up how to glue together the small regions to describe the curvature globally. So it's clear, it should be clear, it's clear to you because it's a leading discussion, but you go from the principle of equivalence, which is this thought experiment, okay, that's very, very physical, very intuitive, very visualizable, and then you get this implication, physics in small regions reduces to special relativity, which sounds exactly like the beginning of differential geometry. Einstein had no idea about this. This was not, some clever story he told after the fact. He got the principle of equivalence, but he didn't know exactly what it meant. He was bouncing around, so between 1905, when he was still a patent clerk, 1915, he was already pretty famous. In between, he was bouncing around. He had gotten his PhD from Zurich, and then he went to Bern, and he went, I think, to Prague, and then he went back to Zurich. And when he was back in Zurich, he's still thinking about this stuff. And so, but he ran into all of his old friends in Zurich because he's got his PhD there. One of his friends was Marcel Grossmann, who was a mathematician. And Einstein describes to Grossmann what he's thinking about. And Grossmann says, yeah, well, you need some Riemannian geometry. And Einstein says, well, what is that? I have no idea. So Grossmann taught Einstein Riemannian geometry. And after some initial reluctance, Einstein eventually says, this is exactly what I need, right? So Einstein eventually says, gravity, the thing that I can get rid of in a small region of space-time, is just the curvature of space-time. Took him a while to actually figure out the equations associated with this motto, but this is the idea. If in a small region of a manifold, you can make the geometry look Euclidean, that's equivalent to saying in a small region of space-time the geometry looks like flat space-time of special relativity, and then the curvature shows up as you go to larger and larger regions, and Einstein says that must be what gravity is, because that's, in this picture right here, you see that the gravity is detectable when you can go to larger and larger regions of space-time. In a small region it disappears, in larger regions it's very, very important. Yet another way of saying the same thing is Einstein is saying that there is a difference between gravity and the other forces of nature, okay? In Newtonian physics, what you would have said is that gravity is a force that lives on top of space-time, and there's an equation for what the force is. There it is, inverse square law, okay? In some sense, according to Einstein, the reason why gravity had been difficult to fit into special relativity is because gravity is not a force. A force you could detect by doing some experiment. If the force is real, you should be able to detect it, but gravity you can't. Not in a small region of space-time if you're locked in that little box. So Einstein says instead of thinking of gravity as a force, what you should do is think of it as a feature of space-time itself. That's why you can't detect it, because everything is in space-time. Everything is affected by the curvature of space-time in exactly the same way. It's not an external force that some things can feel and some things don't. It's a feature of space-time itself. So that's a very, very good perspective. And so, if I'm hesitating because, look, if you were me, right after you first learned general relativity, you would have been one of those people who went around making fun of other people who thought of gravity as a force, because you would have said, no, 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 you're very old-fashioned. Gravity's not a force. Gravity's the curvature of space-time. And, now that I'm a little bit more mature than that, I know that really the answer is who cares? It doesn't matter if you want to call gravity a force or not. If Newton had been right, if all of Newtonian mechanics had been right, the idea of a force was absolutely central. F equals ma, right? It's really an important part of how we define the theory. But he wasn't. We've moved on beyond that now. In quantum field theory, once we get there, we're not doing quantum field theory today, but in quantum field theory, you don't talk about forces at all. There's no F equals ma in quantum field theory. There's just a bunch of different fields interacting with each other. So we still use the word force because it is sometimes convenient, okay? It is not a central part of the ontology of nature. It's a sometimes convenient concept. And that's just as true in general relativity as anywhere else. If someone wants to say the pen falls because the force of gravity is pulling it, fine. Let them do that. Don't be a stickler about whether or not gravity is a force. But you should appreciate that gravity really is the curvature of space-time, because there is one shift of attitude that actually does make a big difference. Let's put it this way. Think of a table. Here's a table. Okay. Again, drawing is not supposed to be the strong suit here, and I'm going to draw a coffee mug on the table. Maybe we're topologists drinking our mug of coffee and not sure whether it's a coffee cup or a donut. Okay. And the coffee cup is just sitting there on the table, right? And you can ask yourself, is the coffee cup accelerating? And this is something that Newton and Einstein would have given genuinely different answers to, because Newton says, no, what do you mean? Of course the coffee cup is not accelerating. It's on the table is on the floor, presumably. Nothing is moving. Acceleration is the rate of change of velocity. The velocity is zero and it stays zero. The velocity is not changing, therefore it's not accelerating. Einstein would say, yes, it is accelerating, because Einstein says that the natural state of motion of objects in space-time is free fall. That is to say, not being pushed by not just a rocket ship engine, but also by a table under you, or if you're sitting down right now, by the chair underneath you, or if you're standing, the floor underneath your feet, okay? He says, look, if you're just standing up, of course you're being accelerated. Even if you're not running or walking, if you're standing still, you can feel the acceleration in your feet, right? That's why you feel heavy. If you're sitting down, you can feel the acceleration in your butt, pushing you upward. The natural thing, so Newton would say, if I moved the table away, the coffee cup would start accelerate and falling, but it's not accelerating when it's just sitting there. Einstein would say it is being accelerated by the table. It's being pushed away from its natural state of motion. And if you quickly remove the table, the coffee cup would undergo its natural free fall motion. So just like inertial trajectories are special in special relativity, unaccelerated trajectories are special. They're just as special in general relativity. They seem curved to us. You know, the Earth goes around the sun. That does not seem like a straight line like an unaccelerated trajectory would be. But what Einstein says is that these trajectories are geodesics, which is a fancy way of saying extremal distance paths. We talked about this when we talked about geometry. One way of defining the generalization of a straight line is to say you have 2 points, you connect them with a whole bunch of different conceptual paths. The shortest one is the straight line, flat space. If you're in curved space or curved space-time, there might not be a straight line in the conventional sense, but there's still an extremal distance path. I would like to be able to say a shortest distance path, but actually it works out to be a longest time path in relativity, so I'm going to say extremal distance, okay? But this is the generalization of a straight line, and this is what objects want to do. In curved space-time, objects want to move on the closest thing they can to a straight line. So the motion of the Earth around the sun in space-time is the best it can do to move on a straight line. It doesn't seem to be straight to us because there are no exactly straight lines, because space-time itself is curved. That's the lesson of general relativity. So you are accelerating right now, unless you just jumped off a building or something like that. Good. So that concludes the truly fun part of our video. Well, it depends on what you mean by fun. Okay, this is the conceptual part. You got it now. You understand the conceptual beginnings of general relativity. Of course, there's more work to be done because we need to mathematize it. We need to turn it into a real, rigorous theory of nature. How are we going to do that? Okay. Well, you need to talk about what is the amount of curvature you have. If gravity is the curvature of space-time, where'd it go? Gravity is the curvature of space-time. Geodesics are extremal distance paths. You need to attach some equations to that. And we know how to do that because we talked about curvature before in the video about geometry. So curvature, the way that we talked about it was in terms of parallel transport. Remember quantum chromodynamics, okay? Remember when we did the gauge theory video? We talked about quarks and how they could be thought of as living in this three-dimensional space of color, red, green, blue. And you might want to parallel transport a certain quark field to some other part of space-time where red, green, and blue might be oriented differently, and you would have a connection field that tells you how to do that. And then you quantize the connection field. The connection field is all over space-time, and the quantum fluctuations in the connection field give rise, in this case, to gluons, or to photons if we were doing QED, etc. And then the connection tells you how to do parallel transport, and then curvature is the failure of parallel transport around a closed loop to bring you back to where you started. So what we mean here is that if we take a vector and we parallel transport it around a little tiny loop through space-time, if space-time, in whatever thing we were moving, like the quark fields or in color space, if you parallel transport them around a loop, if there's no curvature to the gauge field, no curvature to the gluon field connection, then the quarks come back exactly to where they start, okay? But if there is curvature to that connection field, then they might be rotated a little bit, and this is what curvature measures. And the curvature for space-time is special. And this is the beginning of why general relativity is a little bit different than all those other gauge theories. General relativity is absolutely a gauge theory in some very well-defined sense. It is also indubitably different than the other gauge theories, and the reason why is because when we move around a quark, the little vector that is the quark is pointing in a fictitious internal color space. It's not pointing up or pointing left or pointing forward, okay? It's pointing in red, green, blue space, which is a fake space, which we make up to mathematically describe what's going on. Whereas in space-time, you have a trajectory, and the geodesic trajectory is one that parallel transports its own velocity vector, or momentum vector, whichever way you want to put it, okay? So parallel transport, so let's put it this way. Geodesic, okay, straight line equivalent, equals you parallel transport your own momentum, or your own velocity, let's say. That's why it's special, because your velocity or your momentum is a vector that has a direction in space-time, okay? It's not in some fictitious color space. It's pointing up or down or in some linear combination or something like that, okay? So that's why space-time is a little bit different geometrically, and that's good news and bad news, all right? And so we don't need to keep thinking about the geometry of gauge theories because we're interested in space-time right now, but I wanted to let you know that there is that difference there. So in space-time, just like in gauge theories, you have this notion of parallel transport, but there's also an alternative. You also have a notion of distance between points, okay, that is related to the way you have a parallel transporting, etc. This is what is different in general relativity than in other gauge theories. So alternatively, this is one definition of geodesic, okay. Alternatively, geodesic equals, as we just wrote, extremal distance path. So what that means is, we have, again, let's say this is a geodesic connecting 2 points. This geodesic has a length. Let me move it over here a little bit. And the length L, well, what is it? I don't know what it is. You could go and actually measure what it is, but one way of figuring it out would be to divide it up into little segments. Remember differential geometry, we go into tiny little regions, and then we call this little tiny part, we give it a length DL. I'm going to write that as a curved L, because otherwise it just looks like a number 1, okay? So D lowercase script L is the distance along that little tiny bit of the interval, and then the whole length along the path, L, is the sum of all of the little infinitesimal lengths, DL, okay? That's easy enough, that part is easy. The question is, what is DL? How do we know? Like, given some actual path, what do you mean by being given some actual path? You might be given coordinates, okay? Like, there's some coordinates on the sphere, on the Earth, or in space, whatever. If you're NASA, you need to have a coordinate system that extends throughout the solar system. Heliocentric coordinates, if you center them on the sun, for example. Geocentric, if you center them on the Earth. And then you might want to specify your path. You want to tell your path to somebody else. You need to say, here are the coordinates of my path as I travel along it. Okay, so the relationship between coordinates and the path is very important. So what we want is a formula for the infinitesimal distance in terms of the coordinates. And the coordinates, once you're in curved space-time, you can't just say, well, choose right-angled coordinates, choose Cartesian coordinates, okay? Because there aren't any. Like on a sphere, you can't do that. On some wildly curved space-time, you can't do that. So you need a way to do this no matter what the coordinates are doing. You need a perfectly general way of seeing what is this little infinitesimal length. So what we can do is, basically, we alluded to this when we talked about geometry. We can generalize Pythagoras' theorem. Right? So let's imagine that here are your coordinates, and I'm drawing them in some curvilinear way because there's no preferred structure, right angles, parallelism, anything like that. It's an arbitrary coordinate system. Call one of them x, the other one y. What we want to do is figure out what is the distance between 2 points. Okay, and so this is a small bit of x, dx. This is a small bit of y, dy, from here to here. This is dx, there to there, and this is dl, from there to there. So it looks like it should kind of be Pythagoras' theorem, right? dl squared is dx squared plus dy squared. But these are not right angles, and there might be other things going on, so you need to be able to generalize Pythagoras' theorem. And the general formula that you would write down looks like this, and it's going to be a little weird looking, and I'll explain why. So again, the Pythagoras would be, Pythagoras is not right in this case, but it would be dl squared is dx squared plus dy squared. So we want more general, and what we'll do is we'll keep the feature that dl squared scales as dx squared or dy squared. Okay, so if the distances change, you got to square everything. So the more general form
Stanford University.
Is this on? Yes. Well, congratulations. Everybody has survived the midterm, including the TAs so far, who recently have been let out of their entombment with thousands of pages of exam pages. So those are rolling along, and everybody is still awake, so that's good. Okay, so we have now officially entered the second half of the course. And organizational things, readings will now be read, hopefully. Okay, so that's not useful. Books. Now is a good time to actually go and start reading those books. And again, if you are not up to all of both of them, some recommended chapters have come along, and pay attention to those. And again, a subset of you may not know it yet, but about 25% of you will have your life transformed by that chaos book, whereas 25% will resent the purchase price and by forcing you to do this. Also, another major transition here, which is, as far as I can tell so far, I have run out of steam turning the extended notes into actual expository writing. So they're just going to take the form of really poorly organized outlines. And so that happens. Okay. What else? What we now transition to is going to be our strategy for the rest of our course, which is to look at various subjects, and coming down the pike after the lectures today and Friday on sexual behavior will be aggression, competition, cooperation, empathy, potentially language use, schizophrenia. Somewhere in there, there's going to be a week or so on that chaos stuff. But for all of these subjects, we are now going to follow the general strategy. We will start off looking at what the behavior is. And what we're going to try to do there, in addition to looking at it in lots of different species, is to be as objective as any good old ethologist in considering the fixed action patterns of a particular behavior. That established, with the promise that in lots of cases what we think comprise some of these behaviors turn out not to be the case. That established, what we will start is our inexorable march to the left, the timeline that constitutes everything we learn now, stepping back and saying, okay, 1 millisecond before that behavior occurred, what was going on in the brain? What parts of the brain, what neurotransmitters, all of that. Stepping back before that, a second before, a minute before, whatever, what was it in the environment that triggered the brain to produce that behavior? What was the acute releasing stimulus? Stepping back, what do hormone levels that hour, that day, some such time span of that, what acute hormonal exposure had to do with sensitizing you to the environmental stimulus, which released the nervous system into generating behavior, marching all the way back, throwing in culture someplace or other, perinatal effects, early developmental hormonal stuff, eventually considering what do the genetics of the individual, of the population, of the species, evolution kicking in there someplace or other, what do all of these things and something having to do with ecology thrown in there just for good measure, working our way back in each of these cases, understanding what was the biology of 1 second before, 1 minute, 1 hour, 1 million years before that gave rise to it. Back to our two major themes from day one. We are now about to be unbound, unfettered by our buckets, our categorical buckets, and instead explore their interactions. The other being that notion from the very first class, which is at any given point, if we're talking about chronic hormonal effects on this behavior, what we're talking about is the way those hormone patterns were shaped during this period, the way genes contributed to the enzymes that make the hormones, the receptors. The second you're talking about genetics, all of this is becoming apparent. At every one of these points, whatever point we are talking about is going to be the end product of everything to the left and just this temporary sort of footing before going to the things on the right. So this will be our strategy forever after now. So we start off doing this with looking at sexual behavior, the neurobiology, and the endocrinology, and the early experiences, et cetera, et cetera. So to inaugurate the second half of the course, and the fact that it's starting off with lectures on sexual behavior, it has to start off with the stupid obligatory sex joke. Okay, so the Martians come to Earth, and they turn out to be great guys. They're really terrific. They get along wonderfully with Earthlings. All of them like each other a lot. They're all becoming great friends. They pass their hours learning about each other's planets. What's the weather like there? What are sports like here? What are recipes? Everybody's getting along terrifically. And eventually, the Earthlings and the Martians are getting along well enough that they get around to asking the question that everybody's really interested in, which is, well, how do you folks go about reproducing? So the decision is made, the Martians are going to go first, so they clear out a big space, and a whole bunch of Martians come in there, and they stand on top of each other's heads, and their noses flash different colors, and steam comes out of various orifices, and there's clanking noises and whatever, and out pops a new little Martian. And the Earthlings say, wow, that was great, and love the concept, and I got great video of that, and that's terrific, and all of that. Okay, so that's worked out, and now it's the humans' turn. So a willing couple is found and some space is cleared out, and the Martians sit down there with their video cameras as well and clicking away, and this couple goes at it and they finish the whole thing in a sweaty mess at the end, and the Martians say, that's wonderful, that's so interesting, you Earthlings are just endless and they're fascinating things you do, but we have one question though, and which is, so where's the new human? And we said, oh, that takes 9 months. They said, well, why were they in such a rush at the end? So our first question here is, why were they in such a rush at the end? Okay, 3 possible answers. Choice number 1, vote for it. Why were they in such a rush at the end? Number 1, because they were acting with this fervent desire to do something for the good of the species. Just seeing if any hands go up, that's a good thing. Option number 2, doing that because you want to maximize the number of copies of your genes passed on to the next generation. Option number 3, because it feels good. Okay, 1 hand goes up, and I'm not sure what that indicates about everyone, but I will remind you from the survey in the first class there that a far greater percentage of you want to learn about depression than about sexual behavior. So there you have it with the Stanford experience. Okay, because it feels good. And what we deal with here right off the start is this important dichotomy between proximal and distal explanations for behavior. Explanation, a distal explanation for sexual behavior, parentheses, why were they in such a rush at the end, passing on copies of your genes, the effects of hormones and certain reward pathways in the brain, all of that. Proximal mechanism being that it feels good. And starting off, right off the bat, the thing to make sense of with sexual behavior is it is driven by this amazing little loop here of sensory stimuli and feedback and immediate sensations that drive the behavior coming out. And all this stuff down here is for the doctoral thesis somewhere down the line. That's not what the motivation is. Probably more than any other of the behaviors we will look at, the driving forces are very proximal ones. Nobody sits there and figures out how many copies of genes they are passing on and thus are willing to speed up to produce a new human 9 months later. Instead, in species after species, it is proximal motivating mechanisms for generating the behaviors. Okay, so beginning to look at the actual behaviors, there is a funny duality to making sense of sexual behavior across different species, a funny sort of contrast. The first one being that, well, all species go about sex, or all vertebrate species go about sex in a roughly similar way, yet you don't want it to be too similar to the species next door. There's an interesting sort of dichotomy there. All sorts of vertebrate species are doing things with pelvic thrusting and orgasms and, hey, stay tuned, that's coming, and ejaculation and lordotic reflexes and things of that sort, highly conserved fixed action patterns across lots and lots of different species. Nonetheless, amid that, you've got this other problem, which is you want to have these fixed action patterns being specific to your species. You do not want to mess up. So there's this strange simultaneity of very, very conserved basic building blocks of the fixed action patterns of sexual behavior, but along with that, a lot of selectivity within species. Now, how does that selectivity begin to work? What you get is this very interesting interplay, this intercalation between the releasing stimuli and the fixed action patterns. What you get is this chaining of behavior. In other words, the fixed action pattern of one of the individuals constitutes the releasing stimulus for the other individual's fixed action pattern, which constitutes the releasing stimulus for this individual's fixed action pattern, this chaining of transitions there, of interplay between these two, which is where you get the species specificity from. Okay. So in terms of making sense of that, of course, any of this in terms of looking at the general features of how to think about sexual behavior across species, of course, what you have to have out the wazoo is your basic ethology credo of interviewing an animal in its own language about its sexual behavior, wonderfully summarized in this quote by Martha McClintock, researcher. I think I've used this quote already, which is, in her particular case, studying female rat sexual behavior, which turns out to be this very ornate process involving a lot of running around on the part of the female. Studying female rat sexual behavior in a cage is like trying to study swimming behavior of a dolphin in a bathtub. You need to get it in the natural setting, or else you are going to lose all sorts of insight in the particular realm of female rat sexual behavior. The standard picture for decades and decades, the centuries where our finest minds have looked at rats having sex, the standard dogma has been that the female role is a very passive, receptive one. And it turns out it's a very passive, receptive one if she doesn't have enough room to run around and do all sorts of courting stuff on her own, all sorts of proceptive sexual behaviors, which she can't see if you're studying an animal in a setting where they can't speak in their own language. So a big, big sort of vote for ethological principles when it comes to this. All right, so just to get some jargon under our belt right from the start here, in terms of how the professionals talk about sex when they're talking about sex and trying to sound like professionals, here are some of the terms. Old, outdated term, Freudian term that nonetheless has entered the general sort of world of referring to sexual arousal and motivation, libido. Libido, as we will see, that commonplace everyday usage term, is perhaps more technically described as horniness, but can also be described as one term within a trio of the terms that people in the business really use most frequently: attractivity, proceptivity, and receptivity. Quick get to work on poems about those three terms, but what you've got here is attractivity, how attractive an individual is to someone else; receptivity, how receptive that individual is to the interest of the other individual; proceptivity, the active behaviors that are carried out in response to being attracted to. And thus you could say, because of the attractiveness of this organism, this other organism began proceptive behaviors which did or did not prove to meet with receptive fixed action patterns and responses. The very words any of us would use to describe what goes on at a party. Okay, so we've got that triad there, the terms that are much more uncommon than terms like libido or arousal or motivation. These are the more common ones. What is another realm, and terms that are much more used, these are much more zoology terms. What's used far more often in clinical medicine is a description, a dichotomy between motivation and performance. And that is never used more frequently than in the realm of making sense of sexual motivation in men as dissociable from erectile function versus dysfunction, motivation being very, very different from performance. So that's another realm of distinctions. Other realms as well, desire, orgasms, arousal, all sorts of commonplace terms. The performance versus motivation dichotomy and the proceptivity, receptivity, and activity one are the major terms that are used. Next issue in terms of getting to this, how do people find out information about sexual behavior? One option is to sit there with night viewing goggles, and that's very useful for nocturnal species. But how do people find out about human sexual behavior? All sorts of ways over the years, starting with anonymous questionnaires, but a really clever technique was worked out in the 1980s. A biological mathematician named Joel Cohn getting at how to get people to tell you about very embarrassing things about their sexual lives. And this was prompted in the 80s when AIDS first swept in, and it was wildly, wildly taboo at the time in virtually every corner of this country to admit to having a less than standard white bread sexual orientation. Take a look at the extended notes to see the trick that Joel Cohn came up with, a very clever device in order to figure out what percentage of people are doing what sexually without asking anybody to give an answer that they would find perhaps to be embarrassing or grounds for all sorts of persecution. Okay, so beginning to look at aspects of behavior and other features of the sort of rightmost end of all of this. We start off with the most central puzzle in making sense of any of this stuff, which is, so what's up with female orgasms? And we've got right off the bat the simple problem of making sense of this biological phenomenon, and one where fertility is not dependent on it. One does not need to have orgasms to become pregnant, to give birth, to pass on copies of one's genes. So what's the deal with orgasms? First off, a question we will wind up asking with a whole lot of the behavior coming down the line is, are we the only species? And all sorts of careful studies have shown that we are not the only species. Other apes, other primate species as well, monkeys and apes, show orgasm among the females, and that is detectable by all sorts of physiology we'll hear about in a while. We are not the only species. One of the really bizarre, pathetic things about trying to do research in this area was one of the first papers that ever demonstrated something which physiologically was identical to female orgasm in rhesus monkey females, which wound up being a paper in this journal Science. Down there in the footnotes, the authors had to indicate this did not make use of any federal grant money to carry out this study. Just to give you a sense of where some of the stuff sits. Okay, so what's up with female orgasm? It is not necessary for conception. It is not necessary to increase the number of copies of your genes in future generations. Despite that, there is some evidence that it facilitates fertilization. And the technical term that's always been given for that is, bizarrely enough, facilitation. The notion is something about the vaginal fluid, something about the biochemistry of, increases sperm motility. Sperms swim faster and harder and jump upstream back to spawn or whatever it is the sperm are doing with more avidity, with more energetic displays in an environment of more vaginal secretion. And orgasm greatly increases that. So the argument there being that orgasm facilitates fertilization through the sperm facilitation process. Evidence for that has always been a little bit indirect. It is not airtight that that happens. Another argument for why this increases fertility, and this is sort of an interesting one. And the notion here is that what an orgasm does is, among other things, exhausts you enormously, causing you to be far more likely to be horizontal than vertical shortly thereafter, and thus facilitating fertilization because the sperm don't have to swim straight up against gravity. I kid you not, this is one of the leading models out there. Then there's the orgasm facilitates female conception out of reinforcement theory, which is back to the it feels good, and thus you are more likely to do it again and increasing the likelihood of passing on copies of your genes. All of this is wonderful. All of these possible mechanisms where even though female orgasm is not necessary for conception, it nonetheless increases the likelihood of. That's great. However, what most of the studies have shown, though, is there is no relationship between the fertility of a woman and her propensity towards orgasm. It does not seem to play out insofar as any of this facilitation or horizontal swim enhancement techniques or whatever actually occurs. These are not big enough in effects to actually make a difference in terms of reproductive success. So what else? What else is known about it? There is a certain degree of heritability of propensity towards orgasm in females, and this is shown with all our standard behavior genetics techniques in terms of comparing dizygotic versus monozygotic twins. We know what to do in terms of not overvaluing findings like those. Nonetheless, they are there. So, if a basic puzzle is why do females have orgasms if it's not necessary for conception, and in fact the evidence is not great that it even facilitates it, why on top of all of that, why such things as clitoral orgasms, which the studies generally show are more easily brought about than our vaginal ones? What's up with that? Even more of the same questions. Now, somewhere in there is lurking the heartbreaking possibility in making sense of why female orgasm exists, the dreadful possibility that what we're dealing with here is a spandrel. That it is a spandrel. It is simply baggage brought along that those guys have to go through this orgasm physiology to do any stuff with sperm and pass on copies of genes and all of that, and it's simply baggage that the same physiology occurs in females. That orgasm is simply a spandrel in women. And the counter sort of scenario that's always given is this is exactly equivalent to the notion that nipples are spandrels in men, in that women, female mammals, need to go about all this lactation business, and that's part of the whole package deal. And, you know, just as it would be way too much work to evolve females without orgasms, it would be way too much to get rid of those useless nipples on men. Okay, let's have a quick survey. Yes? Okay, so why do males have orgasms? Ejaculation can occur. It is far more voluminous in the face of an orgasm, so that's easily framed in terms of an adaptive mechanism. Okay, quick survey here. How many people, how many guys who have those useless nipples, how many of you go for the nipple as spandrel in guys theory? Whoa, was that slow in the hands? Okay, should I raise my hand? Should I not raise it? Okay, women in the room, how many go for the female orgasm as merely spandrel theory? If I recall, there was one other question somewhere a few weeks back that only got one person fessing up to it and came somewhere around there also. So I don't know if that's the lighting or if people tend to sit in the same places. Okay, so not a whole lot of enthusiasm for these spandrel concepts here. Nonetheless, that needs to be seriously entertained. Okay, so now looking at other features of the fixed action patterns, and amid, all these different species doing lordotic stuff and orgasms and ejaculation, all of that, what are some of the realms of sexual behavior that are relatively unique to humans? First off, one that used to be thought to be absolutely unique was non-reproductive sex. This is a world of difference than those species where the female ovulates for like 2.5 hours every year and everybody mates at that point, or species where somebody comes into heat, a female is an estrus. Humans have non-reproductive sex. And that was viewed as absolutely unique. What is now clear is it is not completely unique. There are lots of other species that do, probably most famously bonobo chimps and various cetaceans like dolphins. Nonetheless, it is certainly a specialty among humans. What else? Foreplay, that used to be in the category of human specialties, and it is clear by now that bonobo chimps, for example, have vastly more patience with foreplay than average humans do. We are not the only species with that either. Huge, huge controversy. How unique is homosexuality to human behavior, human sexual behavior? And what's clear increasingly is we're not the only species with that either. The original view, when people would view homosexual behavior, male-male, female-female, in other species, it would be animals in captivity, and it would be the why is there so much homosexuality in prisons argument, lack of alternatives, this was not normal, natural behavior. What is clear from ethological field studies is we are by no means the only species to have homosexual behavior. What else? One of the things that we do seem to be fairly unique about is having egalitarian sex, which is to say that there are no human cultures where, as part of the central sort of tenets of that culture, people are restricted, only a subset of individuals are allowed to reproduce. And this is a world of difference from various species. For example, New World monkeys, marmosets, there is only one male and one female in a group that does the reproducing. Instead, humans in every culture ever seen have egalitarian sex. What else? What else is highly human? People used to think exclusively so. This endless quest for variety, and again, just take a look at these bonobo chimps, and you'll see how small-minded we are when it comes to this. But something else that is indeed unique to human sexual behavior is the notion that this is something we do in private. There is no other species where the majority of sexual behavior is conducted intentionally outside the sight of everybody else. That is rather unique to humans. What else about human sexual behavior seems to be specializations? One that is fairly unique, if not entirely so, is the subset of humans who psychopathologically confuse sexual behavior with violence, and that seems not to have a whole lot of precedence. So immediately one asks other domains, masturbation. That is not remotely a human specialty. That is all sorts of other species as well. And that used to get the, well, what else is there to do when you're sitting in a zoo? For the animals. What else is there to do? It is not natural, it is a default whatever, but looking out in the real world, and there is plenty of that. And one of the most implausible suggestions for an adaptive just so story thing is why do male primates masturbate to the point of ejaculation? They tend to eat the semen afterward. Whoa, great source of protein. Go the adaptationist, everything has an adaptive basis. This one does not ring terribly true. What else? Fantasy. Fantasy in humans. Is that unique to humans? Obviously, we haven't a clue. But here's one suggestion to me that this is not actually the case. And this was years ago where I was watching my baboons. And there was this one low-ranking kid, this snivelly adolescent kid, with the nearest thing he has ever gotten to a female in his life was some high-ranking female in a bad mood beating on him. And he's sitting there minding his own business, and along comes, I think by any baboon male standards, the hottest female in the troop, who has a peak estrus swelling, is no doubt ovulating that day, comes walking along, followed 2 feet behind by the huge menacing male who was in a consortship with her. And our guy just sits there and doesn't even quite look at what's happening. Every now and then his eyes go up, watching them go past, and as she walks past, he gets an erection and then goes off and masturbates. Okay, the charming, I don't know if this is even the word you can use in this setting, but the charming notion is that we've just seen evidence for some sort of internal fantasy life going on in this guy. Okay, you could be a killjoy instead and say, no, no, she was giving off wafts of pheromones and that was what was responsible for it. Nonetheless, this is about as far as we can get at asking this critical question, are we the only species that does this fantasizing stuff? Marriage. Clearly, we've heard about monogamous pair bonding species. In terms of the formal structure of marriage, it is universal. All human cultures have some version of it. Across all human cultures, more than 90% of people wind up in that culture's equivalent of a permanent, stable relationship. And this is the case in polygamous cultures. We've already heard that business, even though historically the majority of human cultures have been polygamous, nonetheless, amid them, the vast majority of individuals have been in monogamous relationships. Amid that, nonetheless, what is also clear is, amid that highly, highly prevalent pattern of monogamous relationships, there's a lot less monogamy going around than you would think. And this was first sorted out, people like Alfred Kinsey, when first working out that questionnaire approach to people's sexual behavior, what became clear was there's a lot less faith within pair bonding within human species, within humans in this country, and is since shown in all sorts of other societies than one would originally assume. There is social monogamy, but not necessarily anywhere near as high of rates of sexual monogamy. And what the paternity studies have shown is in most Western European countries, the rate at which children have been fathered by an individual other than the person claiming marriageable credit for doing so ranges between 10 and 40% of children. How's that for a number? Okay, what else? What else tends to be a feature of human sexual behavior? What you have is, of course, not only intrinsic in the fact that there's a difference between social and sexual monogamy, you have cheating. That is a human specialty in every culture. What else is absolutely wildly human? This notion of romance. And romance is, by most sort of estimates, a relatively new invention in most cultures, maybe a couple of centuries old. And what is an even newer invention is the notion that romance, passion, etc. should persist, should last throughout the entire duration of a lifetime's marriage. That is an utterly novel concept that is perhaps 30, 40, 50 years old in most westernized countries. That's a new one as well. What that, of course, ushers in is looking at issues of divorce across all cultures. The average duration of marriages are 2 to 4 years. And people have made the argument that that is the typical duration of children being dependent on a high degree of parenting, of both parents being around. That is the average interbirth interval, 2 to 4 years. In most traditional human cultures, what's the term being described then if that is the natural point at which most marriages dissolve and turn into other monogamous relationships? The term that is given is that humans tend toward being serial monogamists, moving from one monogamous relationship to another with, on the average, a lag time roughly corresponding to the interbirth interval. So that's charming. What else? What else do you have? All sorts of other aspects of human sexual variety, but ultimately, when you look at human sexual behavior versus other species, we are so boring. We are so limited when you look at the range of unlikely things going on out there, species that are regularly hermaphroditic. And people, in fact, have done studies on how is it that a hermaphroditic animal does not try to have sex with itself, and these are usually worm-type things, and that's some version of an incest avoidance. At the same time, there are other species where individuals change sex opportunistically, all sorts of fish species where that happens, lots of species that are parthenogenic, where an individual reproduces without the benefit of anybody else's genetic input. Even stranger, there's a bunch of snake species that are parthenogenetic, but the females cannot reproduce parthenogenetically unless they mate with males. They do not actually get any sperm from the males, and they get no genetic contribution, but something about that is necessary for the parthenogenic event to occur. Okay, so all sorts of bizarrities that make our fixed action patterns look really pretty dull, but nonetheless, these are the backbones of the human fixed action patterns, and some of them wildly unique, some of them far less than people used to think, some of them very, very unprecedented. Okay, so what this allows us to do now is make our first big step. What's going on in the brain? What is the neurobiology of sexual behavior producing those fixed action patterns? And what you better bet right off the bat is we are talking about the limbic system. This is all limbic system until we see ways in which it's not just all the limbic system, but it is heavily centered, no surprise, in the limbic system. And this was being noted first around the 1930s, 1940s, with the first experiments where there were lesion studies done damaging different parts of the limbic system in animals. And what would be noted was animals' sexual behavior would change. And this was eventually termed, a profile termed after the two scientists who pioneered this stuff, called the Kluver-Bucy syndrome, which is when you damage some of these strange, mysterious rhinocephalonic sort of structures in there, you change the sexual behavior. You change, for example, in monkeys, whether they are attempting to mate with another monkey as opposed to an inanimate object. They change aspects of the fixed action patterns of the behavior and such. And out of it, this was one of the main driving forces on people saying, nose brain, well, that's great, but actually what we're looking at is a part of the brain that has lots to do with emotion and emotionally related behaviors. That was one of the driving forces on the limbic system being pulled together as a concept. Okay, so what areas within the limbic system are relevant? First pass, there are different hotspots in there depending on gender. Among females, probably the most important area is a subsection of the hypothalamus called the ventromedial hypothalamus, involved in female sexual behavior. What's the evidence for that? Just go back to last Friday's lecture. Lesion studies, stimulation studies, recording studies destroy the VMH. You do not get sexual behavior anymore from a female. Stimulate it and you will get the same behaviors that you would normally only see in an ovulating female rat, for example. All the sorts of tools we heard about. Reinforcing this even more is this is the hot spot in the hypothalamus for receptors for estrogen and progesterone. So that makes lots of sense. Meanwhile, another region of the brain that is typically involved in sexual behavior in females, a region, the midbrain. The midbrain, which seems to have something to do with some of the hormonal aspects of sexual behavior that are specific to females. Finally, back to that lordosis reflex, you got to have a spinal cord to pull off the full array of typical mammalian female sexual behavior. So spinal pathways which do not exist in males. Lordotic reflexes, the back arching reflex, is exclusively a female one. Meanwhile, over on the other side of things, there are regions in the brain that tend to be more specialized for sexual behavior in males than in females. A different part of the hypothalamus called the medial preoptic area. And the exact same sort of evidence is for the ventromedial hypothalamus in females. Lesion studies, stimulation, recording studies, all that sort of thing. And you guessed it, whopping great amounts of testosterone receptors, androgen receptors within the medial preoptic area. Very interestingly, something we will hear more about next week or so is another region of the brain is involved in male sexual behavior, which is the amygdala. That's kind of interesting. The amygdala, we've already heard about amygdala, fear, anxiety, all of that, but the amygdala also plays a very major role in aggression. And there's a small domain of amygdaloid function in males that's involved in sexual behavior, involved in sexual motivation. Medial preoptic area is much more about sexual performance in males. Amygdala is much more about sexual motivation. And all sorts of people have speculated fairly reasonably, I think, that this may have something to do with the fact explaining why among humans it is far more likely to be males than females who go about confusing sexuality with aggression. That it's got something to do with this weird role of the amygdala in male sexual motivation, male sexual arousal. What else? Okay, males have penises, thus they're the only ones who can have penile erections, and to do that, autonomic nervous system. And what we will hear about, what you already heard about in the introduction to the autonomic nervous system, but also in the Zebra's book, is that whole business. In order to manage that, to pull that off, initially this parasympathetic nervous system that establishes the erection. The process of arousal involves the transition to sympathetic, full blast sympathetic nervous system needed for ejaculation. That's what all of that is about, exclusive to males. But then it turns out it's not exclusive to males because it's virtually the exact same physiology underlying clitoral erections in females. The same exact sort of thing, which of course brings up the dangerous possibility of another spandrel in our laps here in terms of making sense of that. I didn't say that just now, did I say that? Spandrels in your lap. Okay. Bringing up that possibility, that is not specific to male physiology. What is specific, of course, is stuff that's going on with penises in terms of blood flow. There's generally a dichotomy between species, between whether or not males get vascular erections or muscular erections. Vascular erections, you increase blood flow into the penis and you stop it from going out the other end, and thus you get vascular-driven engorgement, as D.H. Lawrence would no doubt have described it. Alternatively, in lots of species, there are muscular erections. There is a muscle, for example, found in rodent penises called the erector levi muscle. Well, that's not too surprising that it's called that, and a whole bunch of cell body neurons in the spinal cord responsible for pulling up the sail or whatever it is you do there. And what you get are differences in general. The muscular-driven erections occur a lot faster. The vascular ones, the hemodynamic ones, last a lot longer. Take your pick, but it's essentially the exact same autonomic physiology in both cases. Finally, one other thing, a factoid, a useful one we heard last week, which is insofar as there's very similar physiology to orgasms in both sexes, there's that difference in recovery time. How long it takes for the sympathetic nervous system to go back to baseline post-orgasm, and on the average, a substantial sex difference in that. Yes, everybody managed to guess it last week which direction it went. A far slower recovery time in females than in males. In terms of underlying neurobiology, something that was a major finding in the field were brain regions that differed in size depending on your gender, including in humans. And this ushered in a whole world of sexual dimorphism in the brain. And there have now been shown to be all sorts of brain regions where on the average you get differences in the size of nuclei, you get differences in the number of axons going through a bundle, a fiber, all of that. And we will hear about some more of those down the line. But the one that has gotten the most attention in terms of sexual behavior is a cluster of tiny nuclei in the hypothalamus called the INAH cluster, the interstitial nucleus of the anterior hypothalamus. Do not write down what that stands for, but it's a little nucleus in there, a little subset of neuronal cell bodies where you get a very substantial sex difference in the size of this area, where on the average it is about twice the size in men as in women. And back to the other week's sort of rant about statistical significance versus magnitude, this is a big effect. It is almost in the range where you can identify the sex of somebody by looking at the size of this nucleus in their brain post-mortem. In rodents, you pretty much can. A very reliable twofold difference, males larger than females. As we'll hear in a while, one really interesting exception to that. Okay, so either some areas of the brain that are preferentially involved and activated by sexual behavior depending on your gender, or regions that differ in size substantially by your gender. But then at the end of the day, there's all sorts of things that are absolutely in common. Again, the physiology of orgasm, exactly the same. What clinically the picture is males having problems with the whole system. The problem tends to be too rapid of a transition from parasympathetic to sympathetic. In other words, the world of premature ejaculation. The more typical medical problem in women is failure of the transition from parasympathetic to sympathetic, inability to reach orgasm, and it is, of course, a huge socio-cultural, political, philosophical argument whether that counts as a pathology or normal human variability. I'm not going anywhere near that one, but nonetheless, that is the more common pattern. Neurobiology that's absolutely in common between the sexes, which is all of that stuff at the very beginning of why are they in such a rush at the end, the neurobiology of pleasure and the neurobiology of reward and of anticipation. And this is this whole world of, as we know already, dopamine. The role of dopamine in sexual behavior is virtually identical in both sexes, which is to say it plays a huge role. You find circumstances where you deplete dopamine from the relevant brain regions. Back to last Friday, limbic system, you remember that ventral tegmental area, which sends that big dopaminergic projection to the nucleus accumbens, which then passes it on to all sorts of places in the brain. Deplete that pathway of dopamine, and you're not going to get a whole lot of interest in sexual behavior. You are not going to get a whole lot of libido proceptivity. What's the classic circumstance where you see depletion of dopamine there and loss of proceptive libido? Clinical depression. That's one of the defining symptoms of depression amid the various numerous forms of pleasure that go down the tubes. Loss of sexual interest, one of the defining symptoms. So the dopamine system, the general term given for this is the mesolimbic dopamine system. To distinguish it from some of the other ways the dopamine is used in the brain, the mesolimbic dopamine system is absolutely central to the reinforcing aspects of sexual behavior. So what's the evidence for that? First off, back to that distinction that I think I brought up last week. I wasn't paying attention, but I think I talked about, which is the dopamine system there is not so much about reward, it's about the anticipation of reward. Did I talk about that in monkeys pressing levers? Yes, okay. I should probably read the extended notes at some point or look at the film of this. Okay, what you see there is the dopamine is about the anticipation of, and the dopamine as we heard, is about also fueling the behaviors needed to achieve the reward. Dopamine in this mesolimbic pathway as driving goal-directed behavior. And that is certainly the case with sexual behavior. By now, there's a whole literature involving humans where you stick them in brain scanners and you do something or other sexually arousing or interesting or something or other to them. And then you see what parts of the brain activate, and it's these dopamine pathways consistently way up there, showing just how subtle this can be. How's this? You take men, there's been a whole literature by now showing that you present people in brain scanners with pornography, and that must have been a really interesting human subjects release form you worked out, but showing in both sexes what you tend to see is activation of dopaminergic regions. We will hear in a little while a sex difference in that domain. That will probably not surprise anyone, but how's this for subtle? You take a guy and you show him the picture of someone of the opposite sex, if he is heterosexual, and you show him the picture of this individual, and if it is someone who he assesses as being attractive, you don't necessarily get this dopaminergic pathway to activate. It depends. What this study showed was if the person is making what would pass for eye contact, if they are looking straight out, the dopamine system activates. And if they're looking elsewhere, it doesn't activate. How's that for classic male sort of responsiveness? If it looks as if this attractive person is looking at you, it activates. Even more distressingly from this study, when you show men, on the average blah blah, pictures of women who they would rate as being unattractive, it's when they're looking away that the dopamine system activates. Oh my God, what is going on here? This is pitiful. What also has been shown is the exact same eye contact phenomenon of gay men looking at pictures of attractive men. Another theme we're going to see over and over, which is sexual orientation being pretty much trivial in terms of how it influences some of this neurobiology. Just switch the gender of the other individual and it works exactly the same. Now, when you look at this business about dopamine rising in anticipation of a reward rather than in response to the reward itself, it brings up one of the, it doesn't bring that up, it brings up one of the all-time interesting studies that was published about a decade ago. Okay, so the paradigm I described last week, you put on the light which tells the monkey that, okay, we're starting one of those sessions where if you press the levers adequately, you will get a reward. And they now carry out this behavior. And as a result, they get the reward here. And as we saw, dopamine doesn't go up after the reward. It goes up at this point. This is the, I know how to do this. This is going to be great. This is terrific. Here's where you get the rise in dopamine. This is not only the anticipation, but if you don't have this rise, you don't get the behavior, the goal-directed behavior. Now, in this brilliant study, what they did was transition from a paradigm where, okay, the monkey presses the lever 10 times and gets the reward. Now what you do is the monkey works and it gets the reward only half the time. It gets only a 50% reward rate unpredictably. And what happens to dopamine? Okay, got your choice. What's your vote? It doesn't rise as much. It rises the exact same amount. It rises even higher. Okay, you guys all understand anticipation and goal. It does this. It's one of the biggest rises you will find in dopamine in the brain, short of cocaine. What have you just introduced into there? This is, I'm all over it. I know how this works. This is going to be great. I have mastery and control. I am the captain of my own lever pressing. This is all about that. What's this about? This is what dopamine does when you have introduced the word maybe into the equation. And that is incredibly reinforcing. And people will work like mad in contexts of maybe, far more so than when they work in contexts of certainty. Psychologists have known this forever. This is intermittent reinforcement. You never get more behavior out of an organism than when you have introduced a maybe into it. And part of the brilliance of this study was what they then did. Now animals either got reward 25% of the time or 75% of the time. On a certain level, these are diametrically opposite manipulations. In one, you're getting more rewards, and the other, you're getting less. What's the thing they have in common? They both had smaller maybes than the 50% version, and what you see is it would look like this. 100%, 25 or 75, 50% maximizing the maybe. And one of the most brilliant things that various social engineers do with humans is convince people that there's a 50% maybe when it is not 50% in the slightest. That's what Las Vegas is about. That's an entire world of very smart psychologists making people think in circumstances where there's like 1/10 of 1% of a maybe going on there that is actually a 50%. And when you do that, you get dopamine like crazy and you get goal-directed behavior as a result. Really, really powerful. And this is so strongly the case that this explains an extremely cynical thing that a guy I knew in my dorm back when used to say all the time. How's this for like a dispirited view of what life is like? But possibly absolutely accurate, which is a relationship is the price you pay for the anticipation of it. How's that for a grim worldview? Go figure, this guy had what a string of disastrous relationships, but what you see here is introduce a maybe, and it is very, very powerful. One final piece of the dopamine system here that is pertinent, which is, as you might expect from all of our molecular biology stuff, there's all sorts of different dopamine receptor subtypes. And two of them are pertinent to this world of sexual behavior. Reward, what is called shockingly the D1 dopamine receptor and the D2 dopamine receptor. And what studies show is in monogamous species, what happens is right after mating, when a pair bond is first formed, the second that's over with, levels of the D2 receptor go way down. You down-regulate the levels of the receptor, and you up-regulate the levels of the D1 receptor. What's that about? If you drive down the D2 levels before they even mate, they don't form a pair bond. If you prevent the decline in the D2s after they've mated and pair bonded, or if you prevent the rise in the D1s, they'll pair bond, and then 8.5 minutes later, they'll go and pair bond with somebody else. The D2s seem to mediate the rewarding anticipatory aspects of pair bonding. The D1s on a certain rodential level seem to mediate the pleasure of the monogamous, the truly monogamous features of the pair bond. So very interesting interaction between the two. Okay, one last thing now about dopamine, and this one is like even more depressing than relationships for the price you pay. This was a study which was really like someday may come to haunt you majorly. And in this study, what they did, it was another one of those brain imaging study ones. And what they did was they took people in two categories. In both cases, these are people who had found their beloved. Their beloved, the person who was their soulmate, the person in whose arms they were going to die someday, the person. And they divided it between these two groups. One was a group where they had known the person in whose arms they were going to die for like 2.5 weeks. And the other is when they had been together for more than 5 years. So you pick you put somebody in the brain scanner and you start flashing up at speeds, subliminal speeds of pictures of individuals they know, important control in the study, and embedded in there is a picture of their beloved, and suddenly, somewhere along the way, up flashes the picture of their beloved, be in a short-term relationship, and the dopamine system goes crazy and activates like mad. Now you come back 5 years later into that same relationship with the beloved, and you do the exact same thing, and you flash up their picture, and the dopamine system doesn't activate. What activates instead was that anterior cingulate thing we heard about on Friday, having to do with empathy and comfort and all of that. In other words, what we see here is the neurochemical transition from one's beloved, from causing like your blood to run scalding hot, to your beloved being like a comfortable old armchair. This is one depressing study. So let's take a 5-minute break to contemplate that one. Okay, and then we will resume. Lots of good questions just now during the break. Disappointingly few along the lines of, I've got a friend who, so not a bunch of those, but let's see, a number of questions. First one, can I repeat what I said about the D1 and the D2 receptors? Okay, these are different types of receptors for dopamine. In other words, they all respond to the same neurotransmitter dopamine, but in different ways, and these receptors are found on different neuron types, so you're getting into all sorts of different pathways. What you see is, in rodents, in pair bonding rodents, they better have elevated levels. They better have D2 receptors on neurons being fed by this mesolimbic reward dopamine pathway. They have to have D2 receptors to form the pair bond for the attachment to occur. The second that happens, you need to have low levels of D2 and high levels of D1 to remain faithful in your pair bonded relationship. So what you see in these voles is right after the pair bond occurs, there's down regulation of the D2s and up regulation of the D1s, and if you prevent that from happening, the pair bond that's been formed does not prove lasting. So that's what I was saying there. Somebody brought up the great question, which I was going to say something about and forgot, which is, well, how about like D2, D1 ratios in humans and their sexual behavior stuff? And there's been one study showing that a higher ratio of D2 to D1 predicts more stable relationships. Small effect, not replicated yet, but nonetheless, that's kind of interesting. So on a certain level then, D2 seems to be required, at least shown in rodents. Who knows about us? D2 is about the formation of the attachment. D1 is about the maintenance of it, the faithfulness of it, if you will. Next, somebody bringing up the issue in terms of female orgasm. Maybe what female orgasm is about is a mate selection mechanism, as in individuals who increase your likelihood of having orgasms, or ones you are more likely to lower your D2 receptors for. But the one problem with that one that makes wonderful sense, what the studies tend to show though, is likelihood of orgasm is much more a function of who the female is than who the male is that they are with, arguing against that. Let's see, finally, no, not that. Okay, so we already covered that, and there was one additional question. Okay, so what's the driving force in terms of the proximal reinforcing pleasurable aspects of sexual behavior? What's up with why only some species, us predominantly, have non-reproductive sex, can have sex all the time, versus other species that only do for reproduction? What that means is, in other species, the endocrinology of ovulation is the thing that makes sex pleasurable. And we will see shortly what that's about. In females, it's the hormones associated with ovulation that sensitize various tactile receptors to respond in ways that mediate proximal pleasure. And in males, it's the female giving off, for example, the right pheromones, the right releasing stimuli, driven by the right hormone levels that constitute the proximal signal of pleasurable anticipation. And what you find in humans is it doesn't work that way. You do not need, for example, in women, the elevated levels of estrogen typical of ovulation in order to have tactile responsiveness to sexually arousing stimuli. Stay tuned though, it's easier though when estrogen levels are higher. Okay, final brain region relevant to all of this is the frontal cortex. We already got a first pass at the frontal cortex last week, and frontal cortex regulating your behavior, impulse control, all that sort of thing, gratification postponement, this plays a large role in sexual behavior. What's the easy, immediate explanation that one can come up with? What the frontal cortex does is it makes you be appropriate in your sexual behavior. It teaches you the appropriate context. It teaches you what aspects of proceptive sexual behavior is not a good idea. It keeps you from doing things you would regret vastly afterward. That's a very easy version of it. And commensurate with that, you see lots of circumstances of individuals with frontal cortical damage doing highly inappropriate sexual behavior. One example of it, one of those horrifying things that can happen, this was a case that actually happened in a nursing home in Martinez in the East Bay a number of years ago. This was a man in his 80s who had had stroke damage to his frontal cortex, who was found to have raped a woman there, another 80-year-old with Alzheimer's disease. Damaged the frontal cortex, and all sorts of the "this is not sexual behavior that you do" constraints go down the tubes. Just as importantly, though, what the frontal cortex, with all of its giving you the discipline to do the right thing, some of the time what that takes the form of is getting you to do proceptive sexual behavior. For example, you are trying to do some courtship of some other antlered ungulate that you are courting, and this is terrifying because there's another individual challenging you, and it's the frontal cortex that is getting you to carry out those sexual behaviors at that point, even if it is a terrifying circumstance. Nonetheless, what the frontal cortex mostly is about is reining in sexual behavior. It's not changing the fixed action patterns of sex, it's changing the context in which the fixed action patterns occur. So now we are ready to look at one more feature of the neurobiology, which is when somebody is having sex, what hormonal responses are triggered. Notice this is not here. This is not what hormones have to do with bringing about sexual behavior. This is what are the hormonal responses to sexual behavior. Starting off in females, including human females, having sex increases secretion of progesterone-derived hormones. And that has something to do with reinforcing the pleasure. Interestingly, in females the world over, having sex increases the level of testosterone-related hormones in the bloodstream, androgens. Women, females, generate androgens, maybe 5% the levels you see in males, and they come out of the adrenal glands, and they seem to play a very central role in mediating sexual motivation, sexual arousal in females. How is that shown? Obvious experimental studies with lab rats. How is that shown in humans? When women have any of a number of types of diseases where you have to take out the adrenal glands, sexual motivation, sexual arousal goes down. Give them replacement androgens, and sexual arousal, sexual proceptivity returns. So androgens there playing a role. But probably most importantly in terms of hormones triggered by sexual behavior in females is the release of oxytocin. Oxytocin is really interesting. We've heard about oxytocin twice already. One is when it's coming out of the posterior pituitary, and the second is that minor business the other day, last Wednesday, of oxytocin being another one of those hypothalamic hormones that helps to release ACTH from the pituitary. Remember, it doesn't directly release. It's a modulator of CRH action, if-then clause, etc. But those are the two ways we've heard about oxytocin. Oxytocin also works in the brain as a neurotransmitter and neuromodulator. And what does it do there? It appears to play a very central role in forming attachments, a very central role in forming of pair bonds. And it, along with dopamine and the D2 receptors, are critical for female voles of monogamous species to form pair bonds. Female humans, when having sex, secrete lots of oxytocin and activate oxytocin pathways in the brain, and it appears to play a role in the formation of attachment. Interestingly, as this, a whole body of research now showing that if you introduce oxytocin into the brains of humans experimentally, they become more trusting. Amazing body of research where you take aerosolized oxytocin and you spritz it up people's noses, and what they showed in the studies were, number one type of study, you then play a clip of somebody making an argument for some stance in some debate, and people believe the person more. They find their argument more convincing, they trust the person more. Or the other version that's been shown is you spritz oxytocin up the noses of people and you make them more cooperative in their game theory play. The ways at which they go about playing Prisoner's Dilemma and other games we will hear about later on as well. This has given rise to a whole new field, I kid you not, called neuromarketing. The notion that if only you could spritz oxytocin up the noses of people right before your television ad comes on, they're going to believe you when you say it will make you happy to buy our thing, and they will fall for it. There are actually neuroendocrinologists making a living now selling their wares to neuromarketing people, self-proclaimed ones. No doubt they are spritzing oxytocin up the noses of those, capitalists to get them to hire them to do this, but oxytocin playing a role in this. So that's kind of interesting, because what's oxytocin mostly doing in the body? The vast majority of oxytocin is not the stuff up in the brain in these pathways, some of them impinging on dopamine-releasing neurons. The vast majority is not the oxytocin sitting there in the hypothalamus doing something or other to ACTH in the pituitary. The vast majority is the stuff coming out of the posterior pituitary. And what does oxytocin have to do there? It has to do with milk letdown. It has to do with nursing. And suddenly, instead, it's playing a role in forming sexual pair bonding. And the argument is made that attachment, monogamous attachment, sexual attachment, is in some way evolutionarily a descendant of the neurobiology of mother-offspring attachment. That's where it is originally being driven by. So oxytocin playing a role there as well. Meanwhile, over at the male end of things, up go testosterone levels during sex in a surprisingly linear way. The more sexual behavior in a male, the higher testosterone levels are found afterward. Critically, stay tuned for a little while. These are elevations of testosterone in response to sexual behavior. As we'll see, the evidence that high testosterone levels make males more sexually active is basically non-existent. So critical proviso here. This is sex increasing testosterone secretion, not the other way around. What else? Meanwhile, back to the posterior pituitary. Was that a question? Okay, there's a head scratch. Okay, back to the posterior pituitary, the other hormone coming out from there, vasopressin. And oxytocin is to females as vasopressin is to males. And we've already heard something about this back in the molecular genetic stuff and those if-then clauses and unlikely ways in which you get mutations. Vasopressin also is found in the nervous system, where it serves a neuromodulatory role. And vasopressin is critical for forming a pair bond. Back to that business about when you look at monogamous versus polygamous species, what's going on? What you have uniquely in the monogamous species is expression of the vasopressin receptor gene on neurons that release dopamine. In other words, males secrete vasopressin. And if you are of a species where vasopressin now goes and stimulates dopamine neurons, you decide you really liked having sex with this other vole, and you come back for more. And that's the driving force on the formation of the pair bond. incredible studies showing that if you take male voles from the polygamous species and due to gene transfer techniques, I've mentioned this study already, but you now stick vasopressin receptors into those dopamine neurons, those polygamous males now become pair bonding males. They now become monogamous. So really interesting. What you then see in these studies is you look at these monogamous species where the males have vasopressin receptors on these dopamine neurons, and you look at individual males, and the ones who have more receptors there are forming pair bonds faster. It takes fewer rounds of mating with a female to form a pair bond. So what about primates? So you start off looking at two different primate species, one pair bonding, marmoset monkeys, New World marmoset monkeys, and then one classic tournament species, polygamous primate species, rhesus monkeys. And what you see is you've got the variant, the monogamous vole vasopressin receptor gene variant in the pair bonding monkey species, in the marmosets, and you get the polygamous version of the gene in the rhesus monkeys. So it maps on there as well. So the more of this receptor in these dopamine pathways within monogamous species, the more rapidly they form a pair bond. And what you see is differences in the mere presence of them in comparing pair bonding versus non-pair bonding rodents and monkeys. So how about humans? First thing that comes up is among the apes, you also find the two variants, the monogamous vole variant of the vasopressin receptor gene and the polygamous male variant. So what species do you see it in? In chimpanzees, you see the polygamous vole species version. That makes lots of sense. They are a major polygamous species in their behavior. But then this beautiful dichotomy comes crashing down when you see that you've got the monogamous gene version in bonobos. And as we will hear about in a while, bonobos are the most hyper polygamously, hyper variety-ish sexually behaving organisms on the entire planet. They are as far as you could get from a monogamous species as you can ever ask for if you ask for such things. And you got the wrong type of vasopressin receptor gene. Whatever's going on, it's more complicated than have the version that winds up on the dopamine neurons, and you are going to have 50th wedding anniversaries if you are a vole or you are a marmoset, and it's got to be more complicated than that. So how about humans? And what you see is not explicitly as much genetic variability as some people having the monogamous vole version and some people have the polygamous, but nonetheless you get variation. The gene basically is about halfway in between. Whoa, we keep having that theme over and over. All these different ways of looking at body size and sexual dimorphism and imprinted genes and all that stuff. And humans keep winding up being about a halfway between a classic monogamous pair bonder and a classic polygamous tournament species. So the basic human version of it is somewhere in between. But you get variations. You got genetic variations that either look a little bit more like the monogamous vole version or the polygamous vole version. And what studies have now shown, two different studies independently showing this, have the monogamous vole version, and with a small effect, you are more likely to get married, you are more likely to remain married, and both you and your partner are more likely to rate the marriage as stable and happy. That's kind of interesting. Finally, in terms of the role of vasopressin, in terms of attachment in males, all of that, and in terms of social connectiveness, a large body of studies now have shown mutations in the vasopressin receptor gene. Okay, anybody want to guess what disorder you find it? I put it in the extended notes, haven't I? People have read it already. I know I fell for it last time. I am not falling for that stupid trick again of asking you to prove he sniffed some oxytocin. So does anybody want to guess which the... Okay, what you now all know is there's now been a lot of demonstrations of mutations in the vasopressin receptor gene in family pedigrees with autism, a disease of very, very little attachment to other humans. So we've got written all over the place here some sort of role of oxytocin in female attachment formation and vasopressin, and we've already gotten interesting hints that this applies to humans, and we've already gotten interesting hints that individual differences in the molecular biology of these genes predict something about individual differences in the stability of relationships in humans. Okay, so everything we've been hearing about with the neurobiology, and we're still living in this part, in this bucket here temporarily, has been